This is the 698G. We are at lecture 18. So the experiment that we just did was where multiple people were on a WhatsApp call with full speaker volume. And what happened? What did you hear? It was noise, but was there a pattern to the noise? I mean, it is noise to us because we can't make sense of it. And it was ringing, right? It was slowly increasing, but then eventually it seemed to settle to some ringing frequency, right? So basically, you had a feedback system, right? You had multiple points from which the data was getting sampled and then again fed back through the speaker. So microphone was picking it up, then you were again producing it as an output using the speaker. That got picked up by another microphone, etc. So you had a feedback system, and then that feedback system went unstable, right? And in going unstable, you could hear some ringing in it. So it is sort of like you have set off a oscillation by making this feedback system unstable, right? So this lecture is about oscillators. Which one? Yeah, you can turn on it. So now another example I would like to give you is from a UG lab. So the BTech students had to do a lab, do a particular experiment where on a breadboard, they made a amplifier circuit. So they had this gain stage, they put it in feedback, everything worked fine, right? Now they wanted to increase the gain. So they cascaded multiple gain stages, put everything in feedback, and then connected the output to an oscilloscope. So when they powered on the circuit without any input, right? Can you imagine what was the output? So they had this amplifier circuit, multiple gain stages in cascade. It was put in a feedback, like proper negative feedback, as you have learned. And then they were probing the output of it without any input. Right. So what they actually saw was very clean oscillations. They designed an amplifier, but it turned out to be an oscillator, right? So now, in first part of today's lecture, we will explore how we can make a feedback system unstable so that we can get some useful oscillations out of this, right? So let us now look at a very basic feedback system. Okay, can you give me the expression for y of s by x of s? Please solve. This will be equal to h of s by 1 plus h of s. Okay. Now let's say we want this system to provide us a self-sustaining oscillation, right? Let's say we want oscillation at omega naught. So now let us look at the transfer function at omega naught. So yj omega naught by x of j omega naught. So this is equal to h of j omega naught by 1 plus h of j omega. Right? Now, if I want to build an oscillator, I shouldn't have to give an input at the same frequency, right? Ideally, we want the circuit which, when powered, is giving us the right oscillation. Okay, so my x is 0, x of s is 0, or x of j omega naught is 0. Now, what comment can you make about the this transfer function if my input is 0 and y of s has to be finite, or if this x of j omega naught is 0 and we still need a finite y of j omega naught? So this system needs to have an infinite gain, right? Now, if this system needs to have an infinite gain, that will correspond to the denominator becoming 0. That is 1 plus h has to become equal to 0. right? So now when we solve for this, 1 plus h of j omega naught has to be equal to 0, which gives us the result h of j omega naught should be equal to -1. Now I can write this in terms of the magnitude and the angle of h of j omega naught. So this gives the result. The magnitude of h of j omega naught should be equal to 1. Angle of h of j omega naught should be equal to, it should be equal to plus or minus 180 degree. Okay. So this result is called as Barkhausen's criteria. You might have heard this term already, right? It is also called as the startup condition for oscillation. So you can take notes now itself so that you don't have to go back and listen to this lecture again. And if you want me to slow down at some point, feel free to tell me. Okay, so now let me give you a situation. Let's say I take this function h of s, right? And I feed it with a sinusoid at omega naught. So this is my input. What do I see at the output? So our h of s satisfies Barkhausen's criteria. Okay. So now if I feed a sinusoid at omega naught, what would you expect at the output? So you were saying something? Correct. So now that you know these results, how would the output look like? So let's say this is my sinusoid, input sinusoid. How would the output sinusoid look like? It will be basically delayed by a 180 degree phase, right? So my output sinusoid will look like this, right? Which means beyond this point, the input and the output are simply inverted. Okay, so I'm directly going to show the inverted sinusoid at the output. Is this fine? Okay, so now let me give you another scenario. Let us take our system. So this is h of s, which is satisfying Barkhausen's criteria. The input is 0. And this is basically our output, y of s, right? So now let's say I take this system and I break the loop here. So this is node A, node B. Let's say I inject a sinusoid at this node, right? What do you expect to see in the circuit? So I injected a sinusoid like this. So what happens here? Same signal will come. Okay, so let's go through it step by step in the loop, right? Now here we have a negative sign, which is frequency independent, right? So you'll get the inverted sinusoid here. Now we have h of s, which is providing us a frequency dependent phase shift, right? And at omega naught, it is going to give us a 180 degree phase shift, which means the sinusoid is going to simply get inverted. So whatever I injected at A, the same signal is coming back at B. So now it is possible for this system to sustain the oscillation, correct? Because the same signal is coming around again and again. So this now has a positive feedback, right? Just because there is a negative sign here, it doesn't mean that this is a negative feedback. You also have to take into account the phase that is getting introduced due to h of s. So this will be a frequency dependent phase that is getting added. Therefore, for a particular frequency, this whole system can be in positive feedback. And at that frequency, it is possible to sustain an oscillation. Okay. Okay. Now let us do another experiment. So I take the same system. So this is now in closed loop. And let's say I poke this system with a sinusoid at sine omega naught. Now what would happen? Feel free to discuss. So let's say in the first cycle, I have a sinusoid here. The same sinusoid is going to come here. Then it will go through the feedback loop. So here it will have the inverted sign. And then it's going to get inverted again because of this negative sign. So now in this next cycle, the fed back sinusoid and the next input is going to get added. So now next cycle is going to have double the amplitude. Okay. So now this sine wave, which has double the amplitude, will get fed back again. It gets added to sine omega naught t. So now it will have thrice the amplitude. So this repeats and you will see that your sinusoid will grow. Right? So then you expect to see an sinusoid with increasing amplitude in this case with the same omega naught. Okay. So now we saw that if the Barkhausen criteria is satisfied, it is possible for a circuit to have sustained oscillation. Okay. So let's say I wired up this circuit like with a proper connection. Input is grounded. But another possible state for this whole system is to have zeros everywhere, right? So would it just remain at that state or would you see oscillation? Like if I wired up the circuit and I connected the output to the oscilloscope, would I see an oscillation or would I be able to pick up the 0, 0 state? Huh. Right. So is that clear? So now, usually in circuits, you will have noise present. So we are seeing how the oscillations can start. So the first part is noise. So especially wide band noise. For example, if you have thermal noise in your circuit, the spectrum is going to be wide, right? Which means around your frequency of interest, there is some finite power, correct? So this signal, this power will get amplified by the negative feedback loop, and then it can start to oscillate. Okay. So even if you don't do anything, generally because of the noise of the system itself, it should start the sustained oscillation. Now, another reason could be the sudden disturbances that you do in the circuit. Such as turning on the power. So when you turn on the power, it is as if you are applying a step function to the VDD, which will have all the frequency components, right? So just this act of turning on can sometimes result in oscillation. So if you are doing a transient simulation of an oscillator, right? So in a transient simulation, unless you turn transient noise on, there is no noise present in the system. But instead of a DC VDD, if you give a step VDD, you'll see that it is sufficient to start an oscillation in most cases. Right? Now, the third thing that you can do is to actually force an oscillation using a startup circuit. Right? So this could be forcing two nodes. So for example, if you have a ring oscillator, you might force one node to go to 0 and the other node to go to 1 at the same time, right? So then that can trigger an oscillation and then it will continue. So whatever startup circuit you generally do, it will be active only during the initial phase and then it will get turned off. So that way you don't lose out on much power also. So this is done to initialize the circuit. So far, okay? Okay. So now let's see, given a circuit, how do we analyze to see if that circuit can give us an oscillation? Okay. So we are going to look at the analysis methods. So what would be the first method? So I give you a new circuit, right, with transistors, resistors, etc. You want to analyze whether that circuit can oscillate. So how would you proceed? Okay, is there a generic method? What is top to bottom approach? I mean, in this context? Huh? Okay. But what are you finally looking for? So you can check for the feedback, right? So you can check if the feedback is positive, and if the feedback is positive, then it can oscillate roughly, right? So basically you want to check for the Barkhaussen's criteria, correct? So you identify what is H of S and the frequency independent negative sign. So once you have this, you can directly solve for H of j omega naught equal to -1. Okay. Sorry. So H of S will have the frequency dependence, and the frequency independent negative sign is a minus sign that appears here. Right? So basically you want to look for minus H of S in the circuit. Right? What portion of the circuit is giving you minus H of S? Now, once you can model this, you have to find out the frequency omega naught for which H of j omega naught can be equal to -1. Okay, so this is one of the commonly used methods. Now, another thing that you can do is you force some initial condition on the circuit, much like what you will plan to do with the startup circuit. So maybe if there is a capacitor, you initialize it to some particular voltage, right? Or if there is a resistor, inject an impulse current to it so that it generates an initial voltage, etc. For some initial condition, then see how the circuit is going to respond to it, right? And see if the response of the circuit can lead to a sustained oscillation. Okay, so we'll do examples, then it will become clear. But one quick thing you can think of is, if I have a ring oscillator that is powered, right? It can either oscillate, or what is the other possible state? No, 0 or 1 is not possible for a ring oscillator. If you have even number of inverters, then that can happen. Let's say I take 3 inverters. Right? So either I could have oscillation, which means I'll get 0, 1, 0, this becomes 1 again, etc. Right? So it will oscillate. Or what is the stable state? Midpoint voltage of the inverter. So if all of these voltages are at the midpoint voltage of the inverter, then that is a stable state. It need not oscillate, right? So now in this circuit, you can imagine if I initialized this node to VDD, that is sufficient to create an oscillation, right? So this way you initialize some portion of the circuit and then see how the circuit is responding to that initial condition. Yeah. So force an initial condition. This you do for any node within the closed loop circuit. And observe if the circuit response can lead to oscillation. Okay. Now, what else can you do? Let's say I take the circuit, the full circuit, I pick some node and I inject a sinusoidal current at omega naught. Okay. What comment can you make about the voltage at that node? It will be? So I take the circuit, right? I inject a sinusoidal current at omega naught. Now, if that circuit could oscillate at omega naught, what comment can you make about the voltage at that node? Okay, so I understand the confusion. So let's say I injected I of j omega naught, right? Now I'm asking for V of j omega naught. So if the gain of that system is infinity at omega naught, then this term should go to infinity, right? Which means if I calculate the Z at j omega naught, this should be equal to infinity. So that's it. You calculate the impedance of some node within the circuit. If there is a particular frequency at which the impedance can go to infinity, which means that it's possible for oscillations to happen at that frequency, right? So calculate Z of j omega naught for any node within the closed loop circuit. Find the conditions for Z of j omega naught to be equal to infinity. So these conditions will give you the conditions for oscillations on that circuit. So any questions on the three methods? Now let's take an example. Okay, so here is a circuit with some negative feedback. We have to find out whether this circuit can oscillate. Okay, so we are going to apply one method after the other to see if this can oscillate. So given a circuit, you don't have to do all three methods. You can choose one and apply that. But to get used to these methods, we'll apply all three one after the other. So can you start with the first method? So to find h of s, you will have to start by drawing the small signal model of this. Then find h of s and then see if Barkhausen's criteria is satisfied. So you should have got an h of s as GM into RD parallel 1 by SEL. Okay, so can this oscillate? It can oscillate? Okay, let's check that. So what is the maximum angle of h of j omega you can get? No, based on this equation. How many poles does it have? It has one pole, right? So what is the maximum negative angle or positive angle it can get? Well, put a model. It's basically 90 degree, right? So it can never achieve a plus 180 degree or a minus 180 degree, right? That means this can never go into a positive feedback. The whole closed loop system can never achieve positive feedback for any omega naught. So this system cannot oscillate. So this will not have any oscillations. Okay, now let's see if we get the same result if I apply method 2. So what is method 2? You start with some initial condition and see how the circuit is responding to it. So what is a good initial condition that you can set for this? There is a capacitor. Let's say the capacitor has some initial voltage, right? So see how the circuit is going to behave if you start with some initial voltage on the capacitor. Think for a minute. Feel free to discuss as always. Okay, so let me start with the small signal circuit again. Now the capacitor is initialized to some voltage VC0. Okay. So this connection, right, which is going from its drain to the gate, I'm going to draw it on this side directly. This is okay. Now, is this portion familiar to you? What can I replace it with? I can replace it with a resistor of value 1 by Gm. Okay. So basically, the circuit is, I have a capacitor CL, then I have a resistor RD, then I have another resistor of value 1 by Gm. Okay. So now if I initialize this capacitor to some value at t equal to 0, after that, the capacitor is going to discharge through the parallel combination of 1 by Gm parallel RT. Right? So this also, eventually this capacitor will completely discharge and you won't see any sustained oscillation. Okay, so now can you try the third method? Third method is to calculate the impedance at omega naught. Okay, so our circuit is basically this, right? So if I'm calculating the impedance at this node, this is Z of j omega equal to 1 by Gm parallel RD parallel 1 by j omega Cl. Now, even if I take the magnitude of this, you can see that Gm, 1 by Gm and RD will be finite. And you have something in parallel with finite quantities, right? So this has to be a finite value, right? So Z of j omega is finite for all omega, therefore no oscillation. So we have taken one circuit and analyzed it using 3 different methods, and all 3 methods are showing us that it is not going to oscillate. So now in practice, you pick only one method. So depending on the circuit, maybe one method is more suited than the other. So then you choose that, analyze and see if it can result in an oscillation. Okay, so let me give you another circuit. Let's say you have a delay block and this is giving a delay of delta t. Any voltage signal applied here sees a delay of delta t. No current flows through this block. So check if this circuit can oscillate. And if there is an oscillation, then you have to find the parameters for oscillation. So you can start with method 1. Feel free to discuss again. This is R. So now let me identify the minus H of S. This is what is going to give me minus H of S, right? So H of S is, what is the expression? GMR into e power minus S delta T. So H of J omega naught equal to 1 will give you the condition GMR equal to 1. So that gives you the value GM should be equal to 1 by R. Okay. Similarly, angle of H of J omega naught, this will be equal to minus omega naught into delta T. And this should be equal to minus pi. It has to be equal to plus or minus pi. Since there is a negative sign here and we would like to see omega in positive values, I'm directly equating it to minus pi. So this would give me omega naught is equal to pi by delta T. Okay. So now how do you apply method 2 in this? So you could think of applying an impulse current here. That impulse current will generate an impulse voltage across the resistor. And then you can see how this goes around the loop and check if it is giving you the same results. So I'll leave that calculation to you. We will check method 3 now. Okay. So can you try method 3 and let me know the result? Let's say I apply a test voltage Vx, and let's say this is drawing some current Ix. Okay. So now if this is Vx, what is the voltage here? Vx into e power minus S delta T, right? So the current in this path is Gm times Vx into e power minus S delta T. Current flowing through this resistor is simply Vx by R. And Ix has to be the summation of these two currents. So Ix is now equal to Vx by R plus Gm Vx into e power minus S delta T. So this gives Vx by Ix, which is equal to the impedance at this node. So this is in terms of S. This will be equal to R by 1 plus GMR into e power minus S delta T. So Z of J omega naught is R by 1 plus GMR into e raised to minus J omega naught into delta T. Right? Now, if Z of J omega naught has to go to infinity, the denominator has to go to 0. So we get 1 plus GMR into e power minus J omega naught delta T to be equal to 0, or this should be equal to minus 1. Okay, so now you equate the magnitude and the phase separately. So if I'm equating the magnitude of both, so equating magnitudes, I'll get the result. GMR should be equal to 1. If I equate the phase, I will have the result. So this is minus omega naught delta t should be equal to minus pi. Therefore, omega naught should be equal to pi by delta t. Okay, so we have obtained the same result as before. So now here is an interesting calculation to do. So in this circuit, can you calculate the impedance of the bottom half? So all the portions other than the resistor. So can you calculate the impedance of this portion with delta t here? How much are you getting? 1 by GM into? So now calculate it at omega naught. So you have derived the conditions for omega naught and you have obtained another condition for GMR. Substitute both and then tell me what this impedance is. Let me call this as Z1 of J omega naught. Minus R, right? Or in other words, so if you calculate this, you would get Z1 of J omega. So Z1 of S will be equal to 1 by GM into e power minus S delta T. So if you substitute omega naught to be equal to pi by delta T, so I'm calculating Z of J omega naught. This is 1 by GM e power minus J omega naught delta T. Now omega naught is pi by delta T. Therefore, this simply becomes J pi, right? And this is equal to, if this is e power minus J pi, this is equal to minus 1 by GM. Okay. Now, from the other condition, GMR is equal to 1. Let's say I find out what R is. So this gives me 1 by GM. Okay. So now this whole circuit, I am going to redraw it. Now the bottom portion has a resistance 1 by GM, right? The top portion, which is R, for oscillation, we will make it equal to, sorry, this is minus 1 by GM, this is equal to 1 by GM. Okay. So now another way to think about oscillations is this. So if you have a finite resistance, in every cycle, it is going to dissipate some energy, dissipate some power, which means your amplitude of oscillation should keep reducing from one cycle to the other, right? So you need some component in the circuit that can replenish the energy lost. Okay, so here that is done by a negative resistance of the same value. Okay, so this is another thought process that people sometimes use to analyze oscillation. They see what is the energy dissipating element and then how we can account for that energy lost using some other mechanism, how we can replenish the energy loss. So this way also we can ensure a sustained oscillation. So now a very simple question. We saw that if I want an oscillation at omega naught, I need to have a positive feedback at that frequency. Okay. Now, what happens if I design a system which has a positive feedback at omega naught, but it also has a positive feedback at DC? Can it still oscillate? So the question is, what happens if I have a positive feedback at DC? Every time we have the frequency, that will give the oscillations. Okay. So let me give you a circuit. Can the circuit oscillate? What happens? So what is the feedback at DC? It's positive, and this is simply going to latch up, right? So if you have a feedback at DC, so another quick example that you can think of is, I take 4 inverters, right? This is also going to latch up. So if you have a positive feedback at DC, the circuit is simply going to latch up. So you want a positive feedback for the oscillation frequency, and either a negative feedback at DC, or in case the circuit happens to have a positive feedback, the feedback strength should be much, much smaller than unity. Okay. Any questions on the portions covered so far? If not, we can pause the class here. You can ask if you have any doubts on the project or in the last class.